Hello everyone, in this video we're going to pick up where we left off in section 9.2, subsection 2 here, where we talk about geometric series. So geometric series is a special type of series, and this is the type that it is. A geometric series with ratio r, where r is not equal to zero, is a series of the form. So it looks like starting at n equals to 0. Remember how I said we would start seeing ones that have the starting value at n equals to 0 of a times r to the n, right? And if we look at that for different values of n starting at 0, we would get a, because r to the n is r to the 0 is 1, so a plus ar squared plus all the way up to arn and so on. Right, so that's a super special form of a series, and that's called a geometric series with ratio r. Again, r is the part that's being taken to the nth power. A is the coefficient. Okay, so we have theorem 9.6, which easily allows us to determine whether a geometric series converges or diverges. Right, so if we have a geometric series with ratio r, we know that if the absolute value of r is greater than or equal to 1, then the series diverges. And if the absolute value of the ratio r is less than 1, then the series converges. And even better, we know exactly what it converges to, a over 1 minus r. Right? So every time we look at a geometric series, in order to figure out whether it is convergent or divergent, we just look at the ratio and whether the ratio is greater than or equal to 1, or if it is less than 1. Okay, so if we look at this geometric series right here, it looks like the sum from n equals 0 to infinity of 3 over 2 to the n. So at first glance, we're like, hey, that doesn't really look like a geometric series, right? That doesn't look like a times r to the n, right? But we can do some manipulation, right? So our series here, n equals to 0 of 3 over 2 to the n, well, notice that that 3 is not taken to the nth power, and it's in the numerator, so I can just think about it as a coefficient, right? So in other words, I could rewrite that as 3 times 1 over 2 to the n. Now again, we're like, hey, I see that the denominator of this looks like it should be my r, 1 over 2 to the n, but that's not necessarily any one number to the r, right? It's 1 over 2 to the n, not something to the n, right? But what is 1 to the any power? 1 to any power is just 1. So in other words, I can rewrite this as 3 times 1/2 to the nth power, right? I think I was saying r previously, I meant to say n, right? Because now if I take this guy and if I have a fraction to a power like this, what do? We take the power to both the numerator and the denominator. And again, 1 to the power n, for any value of n, 1 to any power is just 1. So that's back up there, and the denominator is 2 to the n. So we're back where we just were in the previous step. All right, so that's a valid move for algebra. So now we can clearly see what our a and r are, right? So my a, again, is that coefficient, so that's going to be 3, and my ratio r is equal to whatever's being taken to the nth power. In this case, it is 1/2. So now we can tell whether or not this converges or diverges by theorem 9.6, right? So since my absolute value of r, which is the absolute value of 1/2, is equal to 1/2, which is less than 1, we know that it converges, right? And even better, because it's a geometric series, we know what it converges to, right? By theorem 9.6, we know that this converges to a over 1 minus r. What is a? A is 3, r is 1/2. So 1 minus 1/2 is 1/2, so 3 times 2, which would be 6. Right, so this sum is equal to 6. This converges to 6. Okay, now we look at this one. This part B, it's actually already in exactly a geometric series form, right? We don't have to do any algebra. So in this case, my a, my coefficient that's out front that's not being taken to the nth power is just 1, right? And r, the thing that's being taken to the nth power, is 3/2. Right? So again, to determine if this converges or diverges, we have to look at that r. So since the absolute value of r, which is the absolute value of 3/2 in this case, is equal to 3/2, is bigger than 1. Remember, what happens if it's bigger than 1? It diverges, right? So that's really not too fun of an example. Okay, so now let's look at example C here. Example C, upon first glance, you're like, yeah, it looks like the ratio is 1/2. It's gonna converge. Super. And actually, it does converge, right? Because the ratio is 1/2. However, notice that my sum starts at n equals to 4. That formula that gave us this exact sum, a over 1 minus r, was specific to starting at n equals to 0, right? And so when we go to figure out what the sum is actually equal to, we'll have to take that into account, right? So first, again, we notice that a, the coefficient out front, is just 1, and r, which equals to 1/2, right? That's my ratio. So what does that mean? Since the absolute value of r, which is equal to the absolute value of 1/2, which equals 1/2, is less than 1, this converges, right? Cool. But the question also asks to find the sum, right? What it converges to. Well, actually, it just said determine it, but I'm telling you that we should figure out what it converges to, right? So what do we know? We know by theorem 9.6 that this sum from n equals 0 to infinity of 1/2 to the n is equal to 1 over 1 minus r, which r in this case is 1/2. So 1 over 1 minus 1/2 is 1/2, so 2. Right? But again, our series doesn't start at n equals to 0. It starts at n equals to 4. So I know that my series, which is the sum from n equals to 4 of 1 over to the n, when I'm starting at n equals to 4, that just means that n equals to 0, n equals to 1, n equals to 2, and n equals to 3, those terms, those first 4 terms, aren't there, right? So in other words, I could just subtract those terms. So what I'm saying is, if I wanted to look at the series with the first 4 terms missing, I could rewrite it as the whole series minus the first 4 terms, right? And the first 4 terms would be 1/2 to the 0 power plus 1/2 to the first power plus 1/2 to the second power plus 1/2 to the third power, right? Because these are the first 4 terms. And my guy said, hey, let's start after the first 4 terms, right? And now this guy right here, put it in a different color, this one is exactly 2, because that's the sum for n equals to 0, right? So that is 2, and then minus, now these guys I can find because they're just numerical values, right? So minus 1/2 to the 0 power, anything to the 0 power is 1, plus 1/2 to the first power is just 1/2, plus 1/2 to the second power is 1/4, plus 1/8. So 2 minus, all those things added up together is going to give me 15/8, and then 2 minus 15/8 gives me 1/8. So in other words, I found that the series that starts at n equals to 4 and goes to infinity of 1 over 2 to the n is equal to 1/8. Right, it converges to 1/8. Okay, So theorem 9.7 is some properties of infinite series, and basically what it says, if I have two series that the first one adds up to A, the second one adds up to B, they're both convergent, then if I add up, if I do a constant multiple just out front, then I could, in other words, I could factor out that constant multiple from every term, and I would get that it's equal to C times A. So multiplying every term by C is the same as multiplying the whole sum, the final answer, by C. Again, what you would expect. And then the other one here is if I add or subtract all the terms from the first series and all the terms from the second series, then I will end up with the sum of the series A plus or minus the sum of the series B, depending on whether I added subtracted the terms. All right. Okay, so now subsection 3 here is the nth term test for divergence. So this test can only be used to tell if a series is convergent. So we'll talk about, I'm sorry, if a series is divergent. I misspoke. All right, so theorem 9.8. If the sum from n equals 1 to infinity of a sub n converges, then the limit as n goes to infinity of a sub n is equal to 0. Why does that make sense? Well, think about it. If I had this sum that has infinitely many terms, a sub 1 plus a sub 2 plus all the way up to infinity, if these terms don't start getting really, really small later, somewhere down the line for some value, big value of n, then this sum won't converge because I'll just keep adding more and more larger things, and it can't get small enough, the edges can't get small enough to make it add up to some finite term, right? And so that's why in the case, if it's, in this case, if it does converge, then the limit of those terms has to go to 0. In other words, somewhere down the line, my terms have to start getting closer and closer to 0, so that way my total sum can equal something finite. Right? So that is actually where this comes from. And if you know anything about logic or proofs, you know what's called the contrapositive. And this is the contrapositive, theorem 9.9. And this is going to be the one that's actually helpful for us in practice. So what this says is if the limit as n goes to infinity of a sub n does not equal to 0, then it diverges. Right? Notice what it does not say. It does not say that if the limit as n goes to infinity of a sub n equals to 0, then it converges. Right? This is not true. Right? And one of the examples, well, actually, I don't have an example here, but there are plenty of examples that the limit as n goes to infinity does go to 0, but it converges. I'm sorry, but it diverges. Right? Actually, the last example is, now that I think about it, this is going to be one of those examples. Right? So how do we use this theorem? We check and see if the limit equals to 0. If it does, then we know we've got to do more work, right? If it equals to 0, we cannot say that it converges, right? That's not what we can say. But we know if it doesn't go to 0, then it automatically diverges and boom, done. So that's why this test for divergence is a really nice one to start out with, because you can immediately find out if something diverges really quickly. And it's normally a pretty easy test to look at that limit. And if it doesn't, then we'll have to look at one of our other tests that we'll learn about in the next section, right? So example 4, determine if it's possible to use theorem 9.9 on the following series, right? And the only time we can use theorem 9.9 is if the limit does not equal to 0. So here, a sub n is whatever we're adding up, so 2 to the n. So the limit as n goes to infinity of a sub n is equal to the limit as n goes to infinity of 2 to the n, and that equals to just infinity. Right? If I plug in a big number for that, then it just gets bigger and bigger. Infinity is not 0, right? So this is taking into account that first part of the theorem. So since the limit as n goes to infinity of a sub n does not equal to 0, the series diverges, right? And boom, we're done, right? It basically, the way I think about this theorem is if it goes to 0, if the limit goes to 0, then there's hope that it might converge. It might still diverge, but there's hope, right? And so this theorem is basically the one that kills all hope, right? If it doesn't go to 0, then we can just stop. It diverges. We know it's not good enough, right? Okay, so let's look at this next one. The limit is the sum from n equals 1 to infinity of n factorial over 2n factorial, or 2n factorial plus 1. Okay, so a sub n is equal to n factorial times 2n factorial plus 1. Notice that this is not 2n factorial, right? So just be careful of that. So now what are we going to do? We're going to look at the limit as n goes to infinity of a sub n. If this goes to 0, then we can't use theorem 9.9, but if it doesn't go to 0, then we can automatically say it diverges. All right, so let's look at what happens. So the limit as n goes to infinity of n factorial over 2n factorial plus 1. So remember what we can do in this case, properties of limits tells us that we can divide by the highest power of n that appears in every term. In this case, what that means is we can divide by n factorial, divide every term, right? So this looks like the limit as n goes to infinity of n factorial over n factorial over top. Should have made that sign so big. So the numerator is n factorial over n factorial divided by 2n factorial over n factorial plus 1 over n factorial. Simplifying this, I end up getting n factorial over n factorial is 1, 2n factorial over n factorial is 2, and then plus 1 over n factorial, I can't simplify. Now when I look at the limit as n goes to infinity, this piece is going to go to 0, so this whole thing goes to 1/2. Right? So that's not 0, right? The limit as n goes to infinity of a sub n is equal to 1/2, which is not 0, which is exactly what we need to happen for a sub n. Exactly what we need to happen for theorem 9.9. So since it doesn't go to 0, what does that mean? That means this series diverges. And we're done. Okay, so now let's look at this last example. In this last example, like I said, here's the counter example to why you can't automatically conclude if the limit goes to 0 that it converges. All right? So here our limit is, or our a sub n is 1 over n. So I look at the limit as n goes to infinity of 1 over, or of a sub n, which is the limit as n goes to infinity of 1 over n, and that limit is just going to be 0, right? But remember, the only time we can use this theorem is if it's not equal to 0, right? So therefore, we cannot use theorem 9.9, right? In fact, like I said, one would think, hey, it goes to 0, so it converges, since if it doesn't go to 0, it diverges. But that's actually not true. In this case, we'll learn later, the sum from n equals 1 to infinity of 1 over n diverges, right? So this is a case where the limit of the terms we're adding up goes to 0, but it still diverges. All right, so this is the nice counterexample to help you remember that the only time we can use this is when it's not equal to 0. That's why it's called the test for divergence. Okay, that's all I have for this video. Thank you.